So first we want to know our constants. Our triangle is a triangle at t equals 5 seconds. Our x value is always constant at 8 meters, and the height of the triangle is equal to 5 meters. Our z value, or the length of the hypotenuse, is currently unknown. dy over dt is equal to 0.5 meters per second, and that is the rate at which the height of the triangle is changing. The triangle is illustrated below, and we're finding dz over dt, which is the rate at which the length of the hypotenuse changes.
Okay, so for this problem, we have to find dz over dt. Since this is a right triangle, we have to use a Pythagorean theorem, which is a squared plus b squared equals c squared, or in this case, x squared plus y squared equals z squared. So we plug in our values, and we get a squared plus 5 squared equals z squared, or 64 plus 25 equals z squared, and so 89 equals z squared. Now to find z, we have to take the square root of on both sides, and so we get z equals the square root of 89. Now we have to take the derivative in terms of time, and so we get 2x dx over dt plus 2y dy over dt equals 2z dz over dt. And since dx over dt is 0, because it's constant, we get 2y dy over dt equals 2z dz over dt. And so then we plug in our values, so we get 2 times 5 times 0.5 equals 2 times the square root of 89 dz over dt. And so then we have to isolate dz over dt, so we divide both sides by 2 times the square root of 89. And so then we end up with 5 over 2 times the square root of 89 equals dz over dt. And so dz over dt is approximately 0.265 meters per second. So we find that our triangle is closing at 0.265 meters per second. Alright, so for this one, we have to find d theta over dt, which is the change of the angle in terms of time. And so we have time equals 5 seconds, we have x equals 8, and dx over dt is constant, so 0. We have y equals 5 meters, z equals square root of 89. We have dy over dt, which is 0.5 meters per second, and we have dz over dt, which is 0.265 meters per second.
So, the first step to find d theta over dt is to know that tan of theta is equal to opposite over adjacent. So in this case, it would be y over x. We know that the derivative of tan of theta is equal to secant squared of theta, but since we're taking the derivative implicitly, we must also say that we multiply this value by d theta dt. Now, to move on to the derivative of y over x, we must use the quotient rule. And so we get x times dy dt minus y times dx dt all over x squared, because we are taking the derivative implicitly with respect to time. We now know that dx dt is our constant because x is always constant and never changes throughout this problem. Effectively, this means that dx dt is equal to 0, so the y times dx dt effectively cancels out. Next, we can simplify our problem by plugging in values. We know that x is equal to 8 and dy over dt is equal to 0.5. X squared is just 8 times 8, which is 64. And our next step is to solve for secant squared of theta. We know that secant squared of theta is also equal to 1 over cosine squared of theta, which is also equal to 1 over, in parentheses, cosine of theta squared. Using this fact, we can now solve for cosine of theta, which we know is our adjacent over hypotenuse, which in this case is our x over z. Our x value is 8, and our z value is the square root of 89, so we can plug that in, but we must remember that this value must be squared. So the value turns out to be 64 over 89. We must also remember that it's 1 divided by this value, so this value returns an 89 over 64. Now that we've solved for secant squared of theta, we can plug that into our original problem, and we substitute in 89 over 64 for secant squared of theta. We multiply that by d theta times dt, because we still have not found that value. Our next step is to simplify the right side by doing 8 times 0.5, which is equal to 4, all over, and we know that the bottom stays the same, which is 64. Now, we're going to rewrite the left side, 89 over 64 times d theta dt. But now we want to isolate d theta dt, and to do so, we multiply 89 over 64 by the reciprocal, so that's 64 over 89. Those two values cancel out, so 64 and 64 and 89, 89. But we must also multiply the right side by 64 over 89. Luckily, the 64s cancel out, and we're left with d theta dt is equal to 4 over 89. If we want to get the approximation of this value, we get that d theta dt is about 0.0449 radians per second, which in the context of our problem shows that our theta is decreasing by this number as time progresses.